Yeah, my name is Michael Eckel from Fraunhofer SIT and the ATHENE Center. SIT stands for Secure Information Technology. Yeah, I'm a colleague of Henk, so we are working for the same team, let's say. And yeah, today I will give you an overview of TCG Attestation Technologies. So next slide, please. Yeah, that's the content. I think we can skip it. It's quite a lot, but it's just an overview. So we can go to the next slide. I put a bit more information into the slides so that you can share them later, right? So that you can read up on the contents. You are allowed to share these slides, and yeah, there's a couple of links in those. Basically, this picture here is exactly what Hank already explained. It's a bit more simple because I left out the verifier owner and some roles here. And that's the model that we generally have in attestation. In the middle, we have the verifier, which receives evidence from an attester. And there may be different hardware security modules or hardware trust anchors here, like the TPM, the Trusted Platform Module, DICE, the Device Identifier Composition, and BIT. This may be new to some of you. It's called Block Integrated Trust, and it was called MARS before, Measurement and Attestation Routes. So these are all three attestation technologies from the TCG. And as Hank already explained, all of them deliver evidence to the verifier, which in turn appraises this evidence against a reference values, golden measurements, or just a whitelist, let's say, yeah, and produces attestation results, which should be signed or delivered via a secure channel to the relying party, which wants to trust the attester. So basically, the relying party asks the verifier, can I trust the attester? And the verifier replies after an attestation process, um, yeah, yes, it can be trusted, or no, there may be something wrong. Yeah. Sorry, next slide, please. Yeah, yeah, thanks. All of this is based on measured boot. That's a basis for remote attestation. So we have on the left, when we power on a system, the first component that becomes active is the CRTM, the core root of trust for measurement, which measures, performs its main logic, sure, and passes control to the BIOS. But before it passes control to the BIOS or UEFI, I don't know how to pronounce it. It measures it, basically hashes it because it's a piece of software, extends it to the TPM, which basically anchors this in the TPM, and adds an entry, a record to a log, in this case, the boot log, because we are in the boot stage here. The BIOS or UEFI performs its main logic in turn and repeats the same principle before passing control to the bootloader. So measures it, anchors it in the TPM, and puts it in a log, in this case, the boot log. So this principle repeats up to the operating system kernel, in this case, the Linux kernel. And in part of the Linux kernel is the integrity measurement architecture, IMA. Which produces an IMA log. So the kernel stays in control. It doesn't pass control to the OS apps, but the kernel measures all operating system applications that are launched, including also some files read by root. There's a policy in IMA where you can define which parts to measure in which TPM PCR. We could come to this. And produces the IMA log. Next slide, please. This is an example of how such an IMA log looks like. Oh, sorry, there's a slight problem with formatting, but yeah, parts of these components of this log are basically the columns. PCR stands for Platform Configuration Register. TPM has 24 of them. And yeah, IMA typically has PCR10, so this is measured in this register. And on the right, you can see a name, basically a file path usually, but the boot aggregate is a special one. We will not talk today about this, but as you can see here below, bin dash, I think that's it's a shell. It's well known. This is the file path, and this is the file hash. In this case, it's a SHA-1 hash. And this is part of such a log. This is how a IMA log looks like, so that you can, on the verifier side, compare the file path and file hash to your whitelist value, to your golden measurement reference values. Thanks. Next slide, please. This was just an example so that you can see how such a log looks like. Yeah, this is basically the same graphic as before, enriched by some more details on the left in the attester. TPM attestation, sure, you have a TPM, you have the boot log, you have the IMA log, and the one that initiates, the one party that initiates the protocol is the relying party, which wants to know, is the attester trustworthy? So it asks the verifier, which requests attestation evidence. The attester app performs a TPM quote, basically a signature over all PCRs from the TPM, plus some additional information, and returns this, including the boot log and the IMA log. And the verifier then compares all the verifies the signatures and appraises the evidence against the reference values. Sure, you need also certificates or public keys because the TPM signs the evidence with a key that's only known in the TPM, the private part, and the public part must be here on the verifier side. Yeah, in most cases, it's a certificate signed by some CA, and in turn, the verifier returns the attestation result. In the most basic case, yes, trustworthy or not trustworthy, a binary decision. Yeah, thanks. Next slide, please. Yeah, and TPM provides explicit evidence because you can inspect every component and see which component does not match. Device identifier composition engine is another technology by the TCG. It's meant for constrained devices or IoT devices, and it provides implicit attestation. On the left, you can see in blue the unique device secret, which is burned into the device. And then we have the measurement of the first mutable code. So yeah, some firmware. And the hash of this firmware and the unique device secret go into the one-way function, a cryptographic hash engine, hash function. And the result here is the compound device identifier. Yeah, next slide, please. This is DICE's implicit attestation. We can see the UDS, the unique device secret, and first mutable code. Then we have here the CDI, and from this CDI, we can derive a device ID or alias key, some kind of key. In this case, it's an asymmetric key, so that you can boot up this device in your factory and extract the public key, which you ship to your customers, and which you store in your database and ship the device with a private key to the customers. And on the other side of the world, someone brings your device online, and then your device connects to the cloud and identifies with this key, with this private key in a key negotiation process, whatever. Yeah. And if you know the public key, then you can say, yes, it's a trusted device. It has the unique device secret and has booted up this firmware that I expect. And if the key matches, if the signatures match, yeah, then you can derive, yeah, the correct firmware must have booted. So this is called implicit attestation. Next slide, please. Yeah, it's also possible to have multiple layers of dice. In the example before, we had only one firmware. Sure, it can be a modular device and have multiple layers, and every layer can in turn use, instead of the UDS, the CDI as a basis, bringing the next layer of the mutable code, derive another secret from it, and so on. Yeah, that's basically it. Again, I put a bit more information on the slides than I will address here on the spoken track here. So next slide, please. Yeah, this is also an overview of which specifications exist for DICE, and also a link at the bottom, so we can go to the next slide. which is the block integrated trust, short BIT, and it was formerly called Measurement and Attestation Rules, MARS. It's less featured than TPM, but has more features than DICE, because this MARS allows, or BIT allows, for explicit attestation. As you can see, you cannot see my mouse, right? But on the right, the red colored block here, this is the MARS component on internal bus, and it's also meant for integration into constrained and embedded devices like IoT or SoC blocks. Yeah, that's why it's called block integrated trust. And it allows for, it has PCRs like a TPM, so you have explicit attestation, and it has even more features than a TPM. At the bottom, you can see these trusted sensor registers, which are volatile registers that are linked to a sensor, so you can sample sensor data like a clock, temperature sensor, humidity, whatever. So you have hardware information and can include this in your attestations. Yeah, thanks. Next slide, please. This is just, again, an overview of MARS, or in future BIT specifications. And yeah, following the link at the bottom, you get all resources from this working group. Thanks. Next slide, please. Yeah, we were talking about hardware trust anchors like TPM, DICE, and BIT. And the TCG, in addition, also defines or specifies protocols and data formats. In this case, it's called the Trusted Attestation Protocol, which can transport attestation data from a TPM and DICE. TPM, a couple of different formats here. TPM 1.2, which has two different operations, the quote and quote 2. And they all provide explicit attestation. And for TPM2, at the bottom, there's a TPM2 quote, but also we can use an audit session with a nonce or clock data to provide attestation data, like the value, which means the values of the PCRs inside the TPM. And for implicit attestation, sure, we can also use the TPM with a signing key, as long as this key is usable and not restricted by the TPM access policy to this key. We have implicit attestation because the key can be used, so the platform state hasn't changed. And for DICE, we had this before with asymmetric in this case, but DICE also allows for symmetric. There's a specification for this, but we'll not go into details in this talk here. Yeah, and that's basically TAP. Next slide, please. And then we have, for the evidence formats, for the logs especially, we have the canonical event log, which is quite a new spec, I would say. And this unites all existing, it can encapsulate existing measurement architectures like the Linux IMA and PC client boot logs. It can provide them or wrap them into this standard format here. I don't want to go into details, just for you to know that this exists. So next slide, please. And these are the features. Some of them I already mentioned. And yeah, there's multiple encodings or bindings for CEL. Basically, it's defined in a TLV, a type length value structure, but this can be mapped or represented in CBOR, the concise binary object representation, or JSON. Yeah. I think that's it. We can go to the next slide, which is the closing slide. So thanks for listening. And yeah, now I'm happy to answer any questions you may have.
So thank you very much, Michael. Again, very useful. I should also add that Global Platforms TES meets monthly with members of the TCG, and this is a good opportunity to collaborate for those who are particularly interested. Usama.
Yeah, thanks for mentioning. Ira already mentioned this, and yeah, sorry, I never joined these calls, but yeah, I should plan for future meetings. So I think I have the appointment here in my calendar already, but I think I just need to join.
So you have your hand up anyway. Any question or comment for Michael?
Yeah, hello. So I wanted to ask on the TAP protocol that you mentioned. I browsed through the PDF document and it seems that it doesn't define any specific protocol, so to say. So I was wondering
That's
if
true.
it's really okay. It's strange
just
because
I know.
yeah, because it's in the name TAP protocol, and
Yeah.
it was surprising for me that the Trusted Attestation Protocol actually does not define a protocol itself.
This is true, yeah. It's just it doesn't even define the request, just the response. Yeah, nothing
Okay.
else. It's just the response. Yeah, it's not a protocol, and some people argue or ask themselves why it's called trusted. Yeah, it should say TCG Attestation Protocol, but I think there were huge discussions, lengthy discussions about the name. And in the end, it became the Trusted Attestation Protocol.
Right, thanks.
Yeah,
Thank
thanks.
you. So Henk, your hand's up.
Yeah, I wanted to add a little bit to the implicit attestation. Implicit attestation can also be done with TPMs or other roots of trusts-ish things. It just means that some of the evidence, also the claims collected that you could send out to an external verifier, never are sent out from the attester. There is a small co-located verifier inside the attester, and that does the appraisal, and then some signing key for reporting, for generating evidence becomes available. So if the verifier receives evidence signed with a certain key pair, it means that the accessibility of the key pair, already some claims have been appraised on the attester. That is also implicit attestation. And in TPM world, it is a protection profile where you have to reach a certain extent PCR quote. And if that quote is there, you can access the signing key and generate evidence. And that's it. So the TPM actually acts as a micro verifier for a few extensions and then moves on to the actual remote attestation. So that is a real example of local attestation actually happening, which is invisible to the remote verifier.
Okay, thanks for that,
Right,
Henk.
thanks. Yeah.